And we have a very quick survey just about if you have any comments about how the session goes, which I will send again at the end of the talk. And here's the link for that. It's a one question anonymous survey. All right, so without further ado, we are excited to have Laura Starkston from UC Davis telling us about Weinstein Trisections.
Yeah, thank you. So I'm going to share screen by overriding this one. Okay, so now you should all be able to see my notes. All right, well, yeah, thanks a lot for organizing this. This is a nice way for all symplectic geometers around the world to get together. So the project I want to talk about is joint work with Peter Lambert-Cole and Jeff Meier. And so this is about how to understand symplectic geometry regarding in conjunction with trisections, which is kind of a new way of understanding symplectic, or just understanding smooth form manifolds. I just saw a couple of hand raises. Was that still practice? Okay.
Jang, do you have a question? Jang Shuo? Just unmuted you so you can ask a question if you have one.
So maybe I will.
You can continue.
I'll keep going. Okay, so let me just start out talking about Weinstein structures and handles. So I have a little picture here, which is supposed to represent a Weinstein handle. So we know how to build smooth form manifolds with handles by kind of successively taking a ball that we view as dk times d. I'm going to write my manifolds as 2 n-dimensional. And so we kind of think of attaching a handle along the attaching region, which will be the k-1 sphere times d2n minus k, so just a thickened up sphere. And so in smooth topology, we can do this for any k between 0 and the dimension of the manifold. In symplectic topology, in order to be able to extend the symplectic structure over successive handles, we need to keep track of some additional data. And this was what Weinstein wrote down. So Weinstein's construction was a way to ensure that you can extend a symplectic structure over a handle. And the idea is to use a Liouville vector field to identify a collared neighborhood of the boundary. Uh-oh, this shouldn't be bouncing. Okay. And so when I attach a handle, I'm really only concerned with a piece of the boundary near the attaching region. But I can think of, I've got my handle, and I have the attaching region, and then I have the thing that I'm trying to attach it to. And so in order to identify these and extend the symplectic structure, I want to have this Liouville vector field, which is pointing out from one of the pieces and into the other piece. And so Weinstein constructed these kind of model handles, and that's what's supposed to be indicated by this picture. And so this is a picture of this dk times d2n minus k with the Liouville vector field. And so in the k directions, it's pointing inward towards the center. And then in the n minus 2 minus k other directions, it's pointing outward. So we get the RK direction gives us the core, and then the n minus k direction gives us the co-core. And so then in this way, this green region here, this is the attaching region, and that's where the vector field is pointing inward. And the orange region right here, that's where the vector field is pointing outward. So then my resulting manifold at the end will have the Liouville vector field pointing outward. So this is a way to allow us to identify the symplectic structures in a neighborhood of the boundary by just looking at the contact neighborhood of the attaching sphere. Now, there's a significant limitation of this construction, which is that a Liouville vector field is inherently connected to the symplectic form. And so the number of directions in which the Liouville vector field can be pointing inward is constrained to be at most half the dimension of the manifold. So the index of the handles has to be at most n in a 2n dimensional manifold. So this means, in particular, we can't construct a, say, closed symplectic manifold using Weinstein's handle construction. So this is a bit of a limitation in the construction. And if we're interested in studying closed symplectic manifolds, there are various techniques that have been thought about to work in that context. So maybe I'll just ask, are there any questions at this point? I was kind of intentionally a bit vague about the setup of these Liouville vector fields, but I'm happy to answer any questions.
If you have a question, you can click on the Participants tab and then raise your hand.
Okay. Yeah, feel free to interrupt me if you do decide you have a question, but I'll continue for now. So some techniques to study closed symplectic manifolds. One is you can look at Lefschetz pencils. So Donaldson proved that every closed symplectic manifold has a Lefschetz pencil. And so then you reduce the dimension to get a fiber of codimension 2. So if I was looking at a closed form manifold, I'd be looking at a surface fiber, and then I have to study factorizations of the identity in the symplectic mapping class group of that fiber in order to understand my closed symplectic manifold from this topological or symplectic topological perspective. So the complication of that is mapping class groups are pretty complicated, and understanding positive factorizations is a pretty difficult problem. And even in dimension 4, when we're looking at surface fibers, there are some very complicated factorizations of the identity, and some people are very talented in this, but it's clearly a hard problem. Another idea to study closed symplectic manifolds from this Weinstein handle perspective is you can find a divisor in your closed symplectic manifold. So Donaldson tells you that such divisors exist. And then maybe you want this divisor to have complement that can be built from Weinstein handles. And so this decomposition exists on any closed symplectic manifold by Giroux, extending these asymptotically holomorphic techniques of these Donaldson divisors. And so maybe one difficulty with this strategy is that, first of all, the divisors can be very complicated. So this Donaldson asymptotically holomorphic technique gives you some pretty complicated submanifolds, but the complements themselves, even if the divisor is relatively simple, can be quite complicated. So I think I want to just plug this project that I'm working on with a large group of women. So I just changed my screen share to show you. These are some lovely pictures that Angela Wu has drawn. Do you see the pictures? Someone give me, okay. So these are complements of some relatively simple divisors constructed from toric geometry in blowups of CP2. And this is the attaching circle data of not even a super complicated example. And so this is just to give you an indication that complements of divisors can be pretty complicated. Let me just show you the name of authors. So this is with Bahar Achu, Ursula Kaplavia-Searle, Agnes Godblood, Alexandra Marinkovic, Emmy Murphy, and Angela Wu. So you can check that out on the archive, and we have more stuff coming. But let me go back to the project I'm actually focused on today. And so the strategy I want to explain to you today is a kind of third technique. For now, this is in dimension 4, which is a way to understand a closed symplectic form manifold using a decomposition where all of the pieces are actually quite simple. So this is what we're calling Weinstein Trisections. Okay, so this is what I want to tell you about today. Any questions? That was just motivation. So, okay, I'm going to tell you, so Weinstein trisections are trisections, which is a concept introduced by Gay and Kirby for smooth form manifolds. So I'm going to have to tell you what smooth trisections are, and then I'll tell you what the compatibility is that we're looking at with respect to the symplectic structure. So a smooth trisection is a way of dividing up a smooth form manifold into 3 pieces. So this little pie is supposed to be a schematic that indicates how it's broken up. So we have our manifold X is decomposed as the union of Z1, Z2, and Z3. And then the conditions are that the ZIs, these are 4-dimensional one-handle bodies. So maybe I'll just say that as these are diffeomorphic to a boundary sum of S1 times D3s. The number of them can vary. And then the intersections, the pairwise intersections of ZIs, all of my indices are taken mod 3 because this is a trisection. So if I take, for example, like Z2 intersect Z1, what's happening here? My indices are off. This is Z1, Z2, Z3. So the intersection of two of these four-dimensional one-handle bodies, they intersect along their boundary, and that's going to be a three-dimensional handle body. So by definition, this is going to be HI. And HI is supposed to be, this is a three-manifold. This will be a three-dimensional one-handle body, boundary sum of S1 times D2s. And these are all going to be of the same genus. And the reason for that is that the common boundary of each of these handle bodies, which is the same as the triple intersection of the three regions, this is a surface, a genus G surface. Okay, so that is a trisection. And so maybe let me tell you the symplectic aspect that we're going to add on. So if we look at each piece is a four-dimensional one-handle body. So each Zi does support a Weinstein structure. In other words, it can be built from these Weinstein handles. But if I start out with a global symplectic form on X, then I can ask, are the three pieces Zi with the symplectic structure restricted to Zi, are those going to be compatible with the Weinstein handle construction? So we want Zi with its restricted symplectic form to be Weinstein. So explicitly, what we really need to find is the Liouville vector field. And being Liouville means being Liouville with respect to a particular symplectic structure. And in this case, it's the restriction of the global symplectic structure. So find a Liouville vector field. For each Zi, it's going to be a different vector field, which is then, it needs to be pointing outward along the boundary. So pointing outwardly transverse to the boundary of Zi. And so that's the question. So, technically with a Weinstein structure, you're supposed to actually have the additional condition on this Liouville vector field that it should be gradient-like. And in this context, we don't really need to worry about that actually, because our boundary is a connect sum of S1 times S2s, and any Liouville filling of that contact manifold can be deformed. The Liouville vector field can be deformed, keeping the symplectic structure fixed to become gradient-like for a standard Morse function with just index 0 and 1 critical points. So that's the condition that we're asking for in the definition of a Weinstein trisection. So that's the definition. And now I think I just want to give a couple of examples. So on the smooth side, the kind of easiest trisection to look at is if I look at S4, well, a sphere, S4 can be thought of as gluing two 4 balls together along a 3 sphere. So that's not a trisection, but then if I cut one of, like, say, the top 4 ball into 2 4 balls, then I have a 3 ball cutting here. And then I have cut my 3 sphere into 2 3 balls. And I have 3 4 balls. And then the triple intersection, this is a 2 sphere. So that's a trisection of S4.
Laura, I think Hiro might have a question for you.
Okay.
Hi, so how are the Liouville fields supposed to behave near the corners, that is along the sigma?
Yeah, we hate corners, but they're inevitable in trisections. So essentially, you've got each sector, Zi, actually has a corner along sigma. And then what we want to say is there's a way to look at a family of smoothings, like kind of canonical corner smoothings, which limit to the cornered surface, and we want the Liouville vector field to be transverse to those smoothings. I think, you know, intuitively you could also think of having kind of that the corner itself carries a family of tangent spaces, and that you want your Liouville vector field to kind of be transverse to all of those tangent spaces in the positive direction. Does that answer your question, Hiro?
Yes, thank you.
Thanks. Okay. So let me give you, obviously S4 is not a symplectic manifold, so let me give you a symplectic manifold example. So our favorite symplectic manifold is CP2. If it's not your favorite, then I'm sorry. But so CP2 has this nice toric structure. And so I can actually find a trisection in the case of CP2 that's compatible with the toric structure. So I have this triangle, which is the image of my moment map. And above each point on the interior of this triangle, there lies a torus. And so this is going to be my trisection core surface sigma, the triple intersection. And then I'm going to find my 3-dimensional handle bodies by looking at 3 arcs that go from this barycenter of the triangle to the edges. And so over each of these arcs, the preimage under the toric moment map is going to be a solid torus. So this will be my H1, this will be my H2, and this will be H3. And then the preimage over these 3 regions, Z1, Z2, and Z3 are just 4-dimensional balls. So that is going to be a trisection. The KIs are 0, and the genus is 1. And then in this case, this is a Weinstein trisection. The Liouville vector fields, you can actually lift radial vector fields centered at the corners, the 3 different corners. You can lift them from this moment image to CP2 to get an actual Liouville vector field. So for each of the different corners, you can have a Liouville vector field that points outward from each of the 3 boundaries. So notice that these Liouville vector fields are kind of fighting with each other. Like along H1, I have...
Laura?
Yeah, tell me.
Marco Castronovo asks, why do you want sigma over the barycenter?
Oh, I don't care actually where it is precisely. I just need, I I made that as a choice. I need the Liouville vector fields to be transverse, but actually I can change this diagram significantly to move the center around, as long as it doesn't get like too wiggly, so that I still have Liouville vector fields. Does that answer your question? Okay.
He says thanks.
Great. So, okay, we have a Weinstein trisection on CP2, and on each of these HIs, we have one Liouville vector field that's pointing in one direction, transverse, and another Liouville vector field that's pointing in the other direction, transversely. So now I want to just say a few words about diagrammatics, and this is one of the great advantages of trisections, is that, so this is on the smooth side, all of the data of the trisection can essentially be encoded by drawing curves on the surface. So this is my surface sigma, which is this core surface, the triple intersection. And then the curves I've drawn in red, blue, and green are the curves which bound disks in the handle bodies H1, H2, and H3. So I can construct my my form manifold from the inside out. I start with sigma, and then I attach disks along the red curves, and then that will compress to a handle body to give me H1. Similarly, I can attach disks along the blue curves and along the green curves to get my H2 and H3. And then the rule about these curves is that if I look at any pair of colors, this should give me a Heegard splitting, so a Heegard diagram of a connect sum of S1 times S2s, some number. And so then if I combine any of these two handle bodies, that's giving me S1 times S2, and I can fill it in with the appropriate four-dimensional handle bodies uniquely by Laudenbach-Poinarou. So this diagram determines the smooth form manifold. And that's pretty powerful because now we're just looking at curves on a surface. Okay, so in the symplectic context, if we want to keep track of the symplectic structure on the manifold through a kind of combinatorial diagrammatic method, this is more in progress at the thinking level. So the idea is that on each of the handle bodies, you've got these two Liouville structures. One is pointing outward and one is pointing inward. So I've got a Liouville vector field V1, V2, and V3. And if I look at the difference of VI minus 1 near HI, this is going to be symplectically dual to the difference of Liouville forms. So these are the Liouville forms. And this difference, a difference of two Liouville forms, is going to be closed. So this actually defines a foliation on HI. And so this foliation, together with its symplectic areas, is what we'd like to use to try to capture combinatorially the symplectic structure in terms of the kind of diagrammatics of the trisection. So that's kind of work in progress. Let me tell you what we have right now. Any questions right now? So I'm going to give some theorems. So I'm kind of keeping with this smooth symplectic split. So I'm going to start out with the theorem on the smooth side due to Gay and Kirby. So this is kind of the first theorem about trisections, which is that they exist. So every smooth form manifold admits a trisection. So I think that is surprising at first, that you can really just split up any smooth form manifold, no matter how crazy, complicated, exotic it is, into these three very simple pieces. And all of that data can be encoded by just curves on a surface. So the analogous theorem that we're proving on the symplectic side, so this is Peter, Jeff, and myself, is the existence theorem for Weinstein trisections. So every symplectic form manifold x omega, I'm thinking of closed, admits a Weinstein trisection. So a trisection which is compatible with the symplectic structure in this way, that it restricts to a Weinstein handle structure with a Louisville vector field on each of the three four-dimensional one-handle bodies. So that's what I want to tell you a little bit about the proof. Let me tell you just one more theorem and motivation. And question. So on the smooth side, it's a theorem. So I just said something about existence, so the next question should be about uniqueness. So there's a stabilization operation which you can do on a trisection, which changes the trisection but keeps the underlying form manifold the same. So changes the trisection on the same form manifold. And so the theorem is that, in a sense, trisections on a smooth form manifold are unique up to stabilization. So any two trisections on the same form manifold have a common stabilization. So if we take these stabilization operations in the symplectic context, any Weinstein trisection can be stabilized in the same topological way, such that the stabilization is still a Weinstein trisection. So it can be stabilized to another Weinstein trisection. So then you could ask, is the same uniqueness theorem true? Do any two Weinstein trisections have a common Weinstein stabilization? And then this would give us a method to study symplectic manifolds up to symplectomorphism. So this is an open question. Are any two Weinstein trisections? I see something popping up blinking. So if someone has a question, feel free to ask as I'm writing. On same x omega related by stabilization, or do any two have a common stabilization?
The question is from Renata Viana. Can you show that Symington's almost toric mutations are Weinstein stabilization?
Almost toric mutation. Oh, that keeps the symplectic manifold the same, but it's just changing the toric structure. Is that right, Renato?
Yes, that's. Can you hear?
Yeah, I hear you. So
Yeah, I mean, because these you can build these almost toric vibrations. All of these of CP2, you can see these guys with these Liouville domains given as say some sort of neighborhood of these pinwheels. And I wonder if one transformation from one to the other was easy to see as this kind of like stabilizations.
Well,
But Hawking
stabilization.
saying that the genus increased for stabilization.
Yeah, that's right. So the genus does increase for stabilizations. The genus of the trisection surface increases. So it might be interesting to look at those examples and see if they have a common stabilization.
Okay, I see.
But yeah, that's a good question.
Oh, and Johnny is saying that we would have to be gluing by balls.
So the three chunks,
They'll be
the
rational balls.
ZIs,
in this
oh,
example.
they're rational. Yeah, so they need to be one handle bodies. The three chunks need to be one handle bodies. Yeah, so I think those ones wouldn't yield a trisection. Actually, this toric picture is a little bit misleading because the toric picture for CP2 is really the only one which is compatible with a trisection. CP1 times CP1 you can kind of understand through the toric picture, a trisection, but it's not actually, you have to like join two pieces with a little tube. So in general, the toric structure is not super compatible with trisection structure. And these schematic pictures are very much schematic. Like these pie charts are very schematic.
Or you have a couple more questions.
Yeah, so I have the chat open now.
Okay.
So Salman's asking about, potentially using trisections for gauge theoretic results in a kind of easier, more topological way. So I think in many ways the trisection machinery is very much in development right now. The most sort of gauge theoretic result that is out there to date from trisections is Peter Lambert-Cole's reproof of the Thom conjecture using trisections. But I think there are definitely a lot of ideas, and Peter Lambert-Cole is a good person to talk to about this, of some ways in which trisections can be applied to find things about exotic structures that might be obtained normally through gauge theoretic means. Is everyone happy? Okay. So let's see. I think I'm at the point in the talk where I start to do a proof. So this was a good question time. Looks like the chat has settled down. So, with existence proofs, you kind of need a bit of a hammer to be able to say something about all symplectic form manifolds. And so the hammer that we chose to use was the result of Aru and a kind of improvement by Aru and Kotsarkov about symplectic form manifolds being branched covers of CP2. So every symplectic form manifold and by every, I mean every closed symplectic form manifold, admits a map to CP2. And I'm going to avoid talking about almost complex structures as much as possible. But this map at the topological level has some nice properties. So locally, it's modeled on one of the following 3 maps. So I'm writing 2 complex coordinates as my local model. Either it looks like a local diffeomorphism. So this is like a covering map near these types of points, or it looks like a branched cover, a double branched cover. This is the second option. And so the branch locus is the smooth critical locus of this map, which is where Z1 equals 0. Z1 or Z2. It's one of these 2 axes. And then the third map is the cusp. So this is Z1 cubed minus Z1, Z2, comma, Z2. So this is like, it looks like a branched cover at every point except for the origin. And at the origin, it's a slightly worse singularity, which is this cusp singularity. And so we have these kind of 3 models of what the map looks like, and there's some compatibility with the symplectic structure. So the critical locus and its image in CP2, these are symplectic submanifolds, where manifold is being stretched a little bit because the image in CP2, this part is singular, in the sense that it can be immersed and has these cusp singularities. So the image of the critical locus of this type 3 part is going to have singularities which are the cone on a positive trefoil. Okay, and then maybe the last thing that I need to know about the compatibility with the symplectic structure is, well, what happens if I pull back the standard Fubini-Strudi form on CP2? So that pullback, this is not a symplectic structure. This is degenerate. It's degenerate along exactly the critical locus. But there's a way that I can add a small perturbation, which happens to be an exact perturbation. So this is within Roux' paper. So this is actually a symplectic form. So my epsilon can be arbitrarily small. So I'm going to call this omega f. So this is kind of the natural lift of the symplectic form on the base, CP2, to the manifold X. And then I could ask, how does this compare to my original omega? And the answer is that X with the rescaled omega is symplectomorphic to X with this lifted structure. And so I can kind of just work with this omega f, get a trisection with respect to that symplectic form, and then apply this symplectomorphism to get a trisection on X with the rescaled symplectic form. And then the rescaling doesn't affect whether you're a Weinstein trisection or not. So my goal is the general strategy is to pull back the Weinstein trisection on CP2 to a Weinstein trisection on X, kind of with respect to this lifted symplectic form, and then that's going to yield a Weinstein trisection on X with my original symplectic form. Any questions on that strategy? Okay, so there are 3 steps to carrying out this strategy. The first step is that I need my branch locus to be in a good position with respect to the trisection. So I need to isotope the branch locus in CP2 into what's called bridge position with respect to the trisection, the standard trisection on CP2. And isotope means symplectically isotope. And actually, symplectically isotope means ambiently symplectically isotope, CP2. Okay, so I'll tell you a little bit about what bridge position means, but it's basically like a good position of the surface with respect to the trisection, where good kind of means that like the surface is being simultaneously trisected into simple pieces as the 4 manifold. And then we're going to show that once we've put the surface in this nice bridge position, that at the topological level, so at the smooth topology level, the trisection pulls back to a trisection. Under this singular branch covering. And then the last step is to show that at the symplectic level, the Louisville structure pulls back to a Louisville structure. So Louisville structure pulls back to a Louisville structure on each sector. And so that like notion of pulling back is going to be kind of similar to the notion that omega sub f is a pullback of omega. It's not exactly the pullback of omega because that's singular, but we're going to be able to add this little perturbation to make it like, so omega becomes symplectic and so that the Louisville structure becomes Louisville. Okay, any questions? And I'm going to talk about each step. Okay. So bridge position. I want to just say a little bit about what bridge position means. So let's say Q, this is going to denote my branch locus. So this is a surface, like an immersed surface with these cusps. So it's not really immersed, but it's immersed away from the cusps. And then, so what is bridge position? So I want to look at what does the intersection look like of Q with each of the 4-dimensional one-handle bodies, and then the intersection with the 3-dimensional one-handle bodies. So in the 4-dimensional pieces, the intersection I'm going to want to be disks, a union of disks.
I have a question.
Mm-hmm.
But from Silman Agbalut, By branch locus, do you mean the common boundaries of H1, H2, H3?
No, that's the trisection surface. So branch locus, I mean of the map, of this map, F. So yeah, in particular, I'm going to want my surface Q, which is different from my triple intersection of the HIs, to be transverse to that triple intersection sigma. So sigma is Z1 intersects Z2 intersects Z3, which is also the boundary of HI. Marco?
Hi. Do you need Q to have also negative double points, or are positive double points enough?
Negative. So what we get out of Aru's theorem is that potentially we need negative nodes, negative self-intersections of Q. So we are allowing that to happen. And actually when we try to move things into bridge position, what we're using is this Aru-Kotsarkov improvement of the result, which says that you can assume that the surface is braided with respect to a linear pencil in CP2. So if you didn't have negative nodes, then you could make this branch locus Q J-holomorphic, and then up to a diffeomorphism, you could find a J-holomorphic pencil such that the surface is braided with respect to that pencil. Here, we actually need Aru and Kotsarkov's improvement to know that it's braided because it might have negative nodes. But we're pretty much fine with negative nodes in that situation, like as long as we have this strengthening of their result.
Okay, thanks.
So in each four-dimensional piece, this is going to be a union of disks. So we want our surface to look like a bunch of disks. Some of them will have cusps. Some will contain a cusp. And then, as Marco just pointed out, some of them will intersect transversely. And we can assume that they intersect transversely once. So at least what we're going to produce is something where they intersect exactly once, either positively or negatively. And some of them will just be happy smooth disks. And then if you look in the three-dimensional pieces, the intersection with the three-dimensional pieces is going to be a tangle. And we want each of these tangles to be a trivial tangle, which means that it's boundary parallel. So I can isotope it into the boundary surface sigma. And if I glue two of these tangles together for two different HIs, then I'll get the boundary of these disks. So the disks are, if they're smooth disks, their boundary will be an unknot. If they are, so these disks should be not just like general disks, they should be kind of boundary parallel. And if the disk contains a cusp, then the boundary of that disk is going to be a positive trefoil if you consider orientations correctly. So in order to get these things in bridge position, we kind of use the braided structure of the surface to push things around in the trisection. And this little picture at the bottom is a picture from the paper where we're kind of we have our three sectors in CP2. We push everything close to this bottom CP1. So we kind of braid the surface around this CP1 at the bottom. And then we kind of, so the surface is sitting here. And then we carefully push up the singularities, which may be tangencies or cusps or nodes up into this third sector Z3. And so that allows us to kind of split up the surface into a bunch of disks. So that's a quick summary of that. So then once we've put our surface in a good position, then we want to branch cover. So question. Oh yeah, the branch covering is coming from Aru-Kutsarkov. Okay, so this is my attempt to draw a picture of a branch covering. So, okay, I want to say that the trisection lifts to a trisection. Meaning, if I take the preimage of each ZI, which is a 4-dimensional one-handle body, I should get a 4-dimensional one-handle body upstairs. And if I take the preimage of each HI, which is a 3-dimensional one-handle body, that preimage should be a 3-dimensional one-handle body. So each of these things is ensured by this nice bridge position property of the surface. So this is my picture of my downstairs 4-dimensional one-handle body, and then these purple things, this is meant to be the disks of my branch surface. And then I want to say, what's the preimage of this under the branch cover? So what I've drawn up here so far, this is, I took each of these little disks and I isolated them into their own little ball, which gets cut off into a neighborhood of the boundary. And so the rest of it, this part, the map F over this part is just an actual covering map because there's no branch locus. So this is my sort of lame attempt at drawing a cover of this. It's not 100% right, but bear with me. And then now what I need to add in is what are the preimages of each of these little balls. So this first one, which I'm thinking of having a smooth disk inside of it, that's going to correspond to the model of double branch cover, Z1, Z2 goes to Z1 squared Z2. And so when I do that, the chart which contains this critical locus, the chart of this ball, is a ball on which I have a sort of double covering to this ball. So that double covering is going to take this red disk on the boundary where it's attached, and that disk is going to be doubled. So the ball, is going to appear as some kind of ball with 2 red boundary disk components. And then here's the critical locus. And then in my other sheets, I'm just going to have a kind of trivial covering. So just a single local diffeomorphism. If I look at this kind of cusp model, then maybe what I have there is I have this other model. This is the Z1, Z2 goes to Z1 cubed minus Z1, Z2. This is a 3-fold cover, right? And so my red disk is going to lift to 3 disks. And so then I have one ball with 3 disk components. And my singular locus is somewhere in here. It's going to actually lift to 2 components to intersect at the origin of the ball. And so this also kind of serves the role of being a collection of one-handle attachments. In this case, it's like attaching 2 4-dimensional one-handle bodies. And then if I have if I happen to have 2 disks that intersect, each of them corresponds to my branch covering model. And so for each of them, they're going to connect kind of 2 different sheets. So I've got maybe one handle here and then another handle here. So in one of these, one of the disks is the critical locus and the other is just kind of normal. And then in the other disk is the critical locus. So that's kind of the idea of how when I take a preimage under this kind of branch covering, I get 4-dimensional one-handle bodies. And when I look at each 3-dimensional piece, I use the triviality of the tangle to kind of say something similar there. And then maybe because I'm kind of out of time, let me just quickly say something about lifting the Liouville structure. So it's easier to actually lift the Liouville forms instead of the Liouville vector fields. So the point is this omega f is the pullback of the structure on the base plus something which is actually exact. So on Zi, I have my Liouville vector field Vi, and this is going to be omega dual to a Liouville form. And so that form is only defined over the sectors, not defined over the whole manifold. But then if I restrict omega f to Zi, that will equal the pullback of the exterior derivative of that Liouville form. That's basically what the Liouville condition means, is that D of this Liouville form is the symplectic structure I care about. So in this case, d eta I equals omega fubidi stu d. And so then I can look at a Liouville form on the lift, which is just the pullback of eta I plus epsilon times phi. And then the exterior derivative of this is exactly this omega f restricted to Zi. So that's what tells us that the Liouville structure pulls back. And then we need to check that it has the correct structure on the boundary, that the vector field is transverse to the boundary. And that comes from, so V is positively transverse to the boundary if and only if eta, so maybe Vi tilde, if and only if eta I tilde is a positive contact form. So lifting a contact structure under branch covering is something that's well understood. It's in Gygas's book, and it's, if you kind of choose this one form phi appropriately, then this is exactly what you would do to get the pullback of a contact form. And so that's how you kind of show that the Liouville structure on CP2 with contact boundary on each sector is going to pull back to a Liouville structure on the pre-image, which is going to give us the 3 sections of our trisected symplectic form manifold. So that is it. I'm happy to answer any more questions.
Thanks so much, Laura. So if anyone has a question, if you go to the participants tab and you click raise hand, then we can take the questions one by one. Looks like you have a question in the chat or a comment in the chat box.
Okay. Is there a version for symplectic manifolds with boundary? At current, no. So I should say this result is in a paper which is requires like me to spend like 1 more hour of revisions before we submit it to the archive. So it's actually almost done, but that is to say, this is the very beginning of studying symplectic manifolds using trisections. I guess the only other thing that's kind of relevant is Dave Gay did a construction of a trisection from a Lefschetz pencil. And so that's also kind of another way to think about symplectic structures with regard to trisections. But all this is very new. Trisections definitely have versions for symplectic for smooth manifolds with boundary. And I think it would be nice to think about this from the symplectic perspective. It might be that somebody actually is doing that. Maybe Dauphine, I don't know if Dauphine is here or Marco can comment on that, but I think it's a good idea to try to come up with a version of this for symplectic manifolds with boundary. It's not obvious exactly what the structure should be, because now you're going to have 2 different types of boundary on the sectors. The boundary of the symplectic manifold you started with, and then the boundary of the vector, which is on the interior of the symplectic manifold. So I see another question, but did Austin, I saw Austin's hand go up. Do you have a question? Oh, there you go. Okay, so let me just answer the questions in the chat. So first of all, does sigma have some special property in the contact geometry of the boundary? So the sense in which sigma is going to carry, okay, so the contact structure on the boundary can be viewed, if you think about these foliations that I mentioned, coming from the difference of the Louisville structures, then the contact structure can be obtained by perturbing that foliation a little bit one direction or the other. Now, those foliations don't have singularities on the interior of the handle bodies, but if you restrict the foliation to the surface, sigma, then that is going to be a singular foliation on sigma. And so in some sense, you could try to understand the contact geometry of the boundary of Zi in terms of that foliation, in terms of that singular foliation on sigma. But it's definitely, so it happens to be a Lagrangian torus in the CP2 example, but it's always going to be null homologous. So in higher genus, it's never going to be Lagrangian. So that's kind of a somewhat misleading example of how the geometric structure interacts with respect to the surface. So I think the nicest thing you could ask is maybe that the trisection surface, you think of it as a convex surface, and then maybe try to study the dividing set and how the dividing set might interact with the trisection data. But I think that's pretty open. So now I'm gonna look at us. Yeah, right, so convex hypersurface, I think might be a reasonable way to think about it. Now in dimension 4, every surface can be perturbed to be convex, so it's not necessarily saying much about restriction on the structure. So Austin's question, is there a nice characterization of the smooth trisection types which can appear in Weinstein trisections? No. One thing that so that seems like a pretty hard question, because in some sense that would be answering the question of which smooth form manifolds admit symplectic structures. So one thing that we can do is, so part of this project with Jeff and Peter is also extended to a square that we're working on with Juanita Pinzon, Paul Melvin, and Alex Zupan. And so kind of as part of the things we're thinking about in there, we thought about using this branch covering perspective to lift a trisection diagram on CP2 under these types of branch covers to a trisection diagram for the symplectic manifold. And those trisection diagrams can be built in this kind of modular manner by, you have a little piece corresponding to each type of singularity or tangency of the braided surface. And so you could think that every symplectic form manifold has a trisection diagram, which can be built in this kind of modular way. Now, those diagrams are going to have like significantly more genus than they need to, and then you're going to be able to destabilize at least smoothly to simplify the diagram, and then they kind of lose some of the structure of this like nice local model. But I think it's really interesting to try to understand what kinds of characteristics do Weinstein trisection diagrams have, or trisection diagrams that are compatible with Weinstein trisections, that maybe make them special in comparison to a general trisection diagram. So Hero asks, are there interesting ways in which trisections can see holomorphic curve counts? So yeah, that's an interesting question. So I talked about this at Stony Brook a month ago, and Kenji asked me the same question, which is like, can you define some kind of Gromov-Witten invariant in terms of the Weinstein trisection or something? So I think that is definitely hard, and part of the problem, but go for it if you can. The part of the problem is that along these boundaries, you've got convex boundary in kind of two opposing directions. So localizing it to the three pieces of the trisection, it might be a bit tricky because you're doing kind of this convex-convex gluing. I mean, convex-convex gluing can sort of be viewed as flat gluing, but whether this can be understood in some context that works well with respect to pseudo-holomorphic curves, I think is a good question. Okay, question from Oleg. Trying to understand the relation to Giroux's theorem. About decomposing into a divisor and Weinstein complement. So is there a way of going directly from trisections to a Weinstein complement of a divisor? So I think sigma is not a divisor because sigma is not going to be a symplectic submanifold. It's always self-intersection 0. It's always null homologous, so it can't be like point grade dual to a symplectic form. So sigma is definitely not a divisor, but I'm not sure how the trisection decomposition might interact with the divisor Weinstein complement decomposition. Like in a sense, maybe it's kind of analogous to relating the Lefschetz pencil to the divisor. That's maybe a more direct relationship because they're both constructed using asymptotically holomorphic techniques, whereas this is different. So I'm not sure that there is a relation there. As to the second question, like, can I think of these ZI as Weinstein sectors? So sectors as in GPS sectors. I think maybe, but I'm not, well, I mean, they're Weinstein manifolds, but with respect to a choice of Weinstein structure. And whether you want to change the Weinstein structure so that you put some kind of stops somewhere, you have to figure out where you want to do that. If you're going to try to define some holomorphic curve locality something. Marco, do you understand what happens to Weinstein trisections under blowups? It is understood by, for example, Jeff Meier, how to understand a trisection under blowup, and there's, I believe, some understanding of fibersum. Okay, Peter, thank you. Yeah, it's great to have collaborators in your talk. Okay, so Jeff is telling me that blowup can be done preserving the Weinsteinness of the trisection. And as to fibersum, I don't know immediately. Yeah, so I think we'd have to think about that. We have to think if fibersum can be done compatibly with Weinstein trisections. Any other questions? Or like people who already asked a question and I didn't sufficiently answer it? Zach? You have to unmute yourself to talk. I'm not even sure if you're capable
Oh.
of unmuting yourself.
How's this?
Oh, yeah. Okay, I hear you.
Sorry, there are 2 mute buttons I have to click. So what does can you describe a neighborhood of the attaching locus? So it looks like it's like something with 3 concave contact ends, and should I think of that as like a simultaneous cap for the 3 Weinstein things?
So I have 3 pieces that are being glued along like partial boundaries. So I've got like, yeah, maybe 2 pieces, which each of them has like a convex boundary. But I could kind of view half of either of those boundaries as concave, and then glue them along the half boundary, which is a 3-dimensional handle body. So the attaching locus is like a wedge of circles. I'm not sure I'm answering.
No, so we have 3, I mean, we've got sigma and the 3 3-dimensional handle bodies filling it.
Oh,
So that's a kind of some 3-dimensional stratified thing, and that has a neighborhood in the symplectic manifold. So I'm asking about that.
So yeah, once I understand the symplectic structure on this kind of spine, the 3-dimensional object, and then I can kind of extend that to a symplectic structure on the neighborhood, then I've just got a bunch of concave connect sums of S1 times S2s, and that I can fill in with a handle body. So there's a unique filling, which is this boundary sum of S1 times D3s,
smoothly, right?
symplectically in this dimension.
Okay.
So there's a unique filling, but there's some question of like, does every contactomorphism of the boundary uniquely extend, or does every contactomorphism of the boundary extend to a symplectomorphism of the interior? So in the smooth category, this is Laudenbach-Poincaréu's theorem, that every diffeomorphism of the boundary extends on the interior. And I have really wanted to use this analogous result in symplectic topology in like 3 different contexts. And from what I understand, although I can't quite find it in the literature exactly, there's some kind of holomorphic disk filling techniques that start to get at this, and a number of papers by Gygas and collaborators get sort of very, very close to proving this statement. So I think that the symplectic version is probably true if it's not exactly written in the literature. It's sort of almost written in the literature.
And so I guess going back to the earlier question, like, if we wanted to study holomorphic curves here, do you think like there might be some kind of Borman-Sheridan class associated to this like tripod at the top?
Possibly. Yeah, I mean, yeah, it could be that what you really want to do is figure out what the tripod is, like all the interesting information gets sort of localized onto the tripod. Yeah, in a sense, that is kind of splitting it into a convex piece and a concave piece, where the convex piece happens to be disconnected, but fine. And then the concave piece, instead of being a divisor exactly, it's this kind of 3-dimensional thing with corners. So yeah, maybe there's an interesting way to associate a kind of Borman-Sheridan class, or like something keeping track of that concave symplectic manifold.
Okay. Thanks.
Any other questions?
So we were thinking if we could end here, and if there are any more questions, people could stay in the room and ask you afterwards.
Sounds good.
All right. Let's thank the speaker virtually. There's a clap button. next to the raise hand button if you want to click that. Thank you again, Laura.
Yeah, thank you.
Thanks.
Laura and Zach.
Mm-hmm.
Zach is still around. Oh yeah,
I'm still here. Yeah.
So what you were saying